Okay, so we're going to look at differential equations like this one, which when you solve this using the auxiliary equation method, you get repeated roots. So here we would get a repeated root of -3. So instead of our solution just being a e to the -3 plus b times e to the -3, we're all taught that we need to introduce this extra x term here. So we have a plus bx times e to the -3x. So we're going to really focus on where has this extra bx term come from, because this looks quite different from what we get in the case where we have distinct roots for our auxiliary equation. And we'll look at a few different ways of understanding this, so see which one's your favourite. And for our first way of understanding this, we're actually going to look at the case to begin with where we've got distinct roots, and then see how this derivation, this proof, can be adapted when we have repeated roots. So if I just write out an equation which would have solutions with distinct roots, let's write it, and I'm going to use just the y prime notation rather than d2y by dx squared, and this is dy dx. So if we had this differential equation, this one would have solutions, because alpha and beta are going to be our two roots of the auxiliary equation here. Our solution is going to be the form y equals a e to the alpha x plus b e to the beta x, and this is our general solution to this, where capital A and capital B are our arbitrary constants. And these are effectively coming from the auxiliary equation, where we just replace our second derivative by lambda squared, our first derivative just by lambda, and we replace y just by 1. So this quadratic equation has roots alpha and beta, which then we put into our exponents there. So where has this method come from? Well, one way of understanding this is just to substitute this back into the original equation, and you see that it works. But I don't think that gives much insight into how we could come up with this, like where has this actually come from, because you would need to know what to substitute in to check. So there's quite a nice way of seeing this, where if we think about this like solving the quadratic, where you've got roots alpha and beta, we could apply this method of splitting the middle term here. So we could split this middle term, minus alpha y prime minus beta y prime, into two separate terms. So we can rewrite all of this as the second derivative minus alpha y prime minus beta y prime plus alpha beta y equals 0. And then we're going to focus on each of these pairs of terms, and we can factorise these effectively. So for the first two, we're going to write this as, since they're both derivatives, we can actually write this as the first derivative of y minus alpha times y, then the derivative of all of this. So this is the same expression. And similarly here, we can take out a factor of negative beta, and then we're left with y prime minus alpha y in the brackets. And can you see we've got the same expression inside the brackets there, our y prime minus alpha y in each of those. So if we define this, let's call this u for a substitution. So we introduce a new variable u, which is y prime minus alpha y, then we get the expression becomes u prime minus beta times u. And remember, u prime just means du dx. So this is all differentiating with respect to x, and this is all still just equal to 0. So we've now got a much simpler differential equation which we could solve, and there's a few different ways of doing this. You could solve this using the integrating factor method or using separation of variables. So hopefully if you're at a stage where you're interested in second order differential equations, we can just build on our knowledge of using first order differential equations like this. So I won't go through the steps here, but we're going to get as our solution u equals some constant, which we'll call a, times e to the beta x. So this is our general solution in terms of u, but remember u is actually this y prime minus alpha y, so we still need to do some more work to get our general solution in terms of y. So now, remembering that we defined u as y prime minus alpha y, we can write u as both y prime minus alpha y. We also know that this is equal to a e to the beta x, where a is just some arbitrary constants. And now we've got a differential equation which we can solve to find y. And this is again in the form where we could use the integrating factor technique, for example. So here, because we've got negative alpha times y, our integrating factor is going to be e to the integral of negative alpha dx, which when we integrate this, we just get e to the negative alpha times x. So this is our integrating factor. So we multiply all of the terms on both sides by e to the negative alpha times x. We get e to the negative alpha x, derivative of y, minus alpha e to the negative alpha x times y equals a e to the then beta x times e to the negative alpha x, or factorise as e to the beta minus alpha times x, like this. And the reason we've done this, the integrating factor tells us now that these two terms are actually a single derivative of a product. So this is how the integrating factor method works. So we can write this as e to the negative alpha x multiplied by y, just the derivative of this product. So you can see using the product rule you would get back to the original expression. This is still equal to a e to the beta minus alpha times x. So now we can just integrate on both sides, and this will introduce another constant. So integrating on the left-hand side, we get e to the negative alpha x times y, and we'll take our constant on the right-hand side. When we integrate this, we're going to have a over beta minus alpha times e to the beta minus alpha times x. So you can see here this division by beta minus alpha, this integral is only really valid when alpha and beta are distinct. We'll return to this later in a moment when alpha and beta are the same root, where we have this repeated root. So this is valid when we've got distinct roots, and we've integrated this, and we also have plus some constant, so plus an arbitrary constant c. So now to get y on its own, we just need to multiply on both sides by e to the alpha x. So we get y equals a, and then here we've got e to the beta minus alpha x times e to the alpha x just gives us e to the beta x. And don't forget we're still dividing this by beta minus alpha. And then we've got plus c, so c gets multiplied by e to the alpha x as well. And now we can just relabel our constants. So we could call this one a, or we could call this a prime since we've already used a. And this constant a over beta minus alpha we could just define to be b. So then we get our general solution is indeed this form that we were looking for. Y is a prime e to the alpha x plus b e to the beta x, where your a prime and your b are just arbitrary real constants. And now let's try and do the same argument, but where we've got repeated roots. So if our differential equation has a repeated root alpha, then this is what the general form of the differential equation would look like. And just like before, we can do this trick of splitting the middle term up into, we'll get y prime prime minus alpha y prime minus another alpha y prime plus alpha squared y, and this is equal to 0. Then we can pair up each of these terms, so we can write the first two as a derivative of y prime minus alpha y, so the derivative of this, and then the second one we can factorise with negative alpha and y prime minus alpha y. This is all still equal to 0. So just like before, we've got this y prime minus alpha y in both of the sets of brackets. So if you just define this as u is y prime minus alpha y, then we've transformed our differential equation into the nice u prime minus alpha u equals 0, where this is differentiation with respect to x still. And we can solve this again using the integrating factor technique or using separation of variables, and we'll get the general solution for this differential equation will be u is some constant, which we'll call b, times e to the alpha x. So now we know that u is y prime minus alpha y, so we can write this as y prime minus alpha y equals b e to the alpha x. And now we can solve this differential equation to find y, again using the integrating factor technique. So our integrating factor, we need to do e to the integral of this negative alpha term, so negative alpha with respect to x, and this just gives us e to the negative alpha x. So we need to multiply on both sides all the terms by e to the negative alpha x for the integrating factor technique to work now. So we get e to the negative alpha x derivative of y minus alpha e to the negative alpha x times y, and then the right hand side is quite interesting. So we have b times e to the alpha x, and we multiply by e to the negative alpha x, so we actually just get b. And if you contrast this step to what we had when alpha and beta weren't equal to each other, where we had distinct roots instead of a repeated root alpha, at this stage we actually had b times e to the beta minus alpha times x. So we just keep a note of this. This is what we had in the previous case, so we can compare in a sec. So here, because we've used the integrating factor technique, the whole point of this is that we can now write this as the derivative of a single product on the left-hand side. So we've got e to the negative alpha x times y, just the derivative of all of this with respect to x, is equal to b. So now we can integrate on both sides, and we're going to get e to the negative alpha x times y is equal to, when we integrate this constant b, we're going to get bx plus another constant which we'll call a. So now it's just a simple matter of making y the subject. So we multiply on both sides by e to the positive alpha x. And if we rearrange these two terms, we'll write this as a plus bx rather than bx plus a. We multiply this by e to the alpha x. You can see now where this solution has come from. It's quite nice that you can see where this bx has come from. It's come from integrating this b, whereas in the case where we have distinct roots, we're integrating b times e to the beta minus alpha x. So this is going to give us a completely different integral when we integrate compared to just integrating a constant, which leads us to the bx term, which we now have some more understanding of where it's come from. And now for a second way of understanding where this bx term comes from, we're going to draw on our knowledge. Let's imagine that we're already convinced that y equals some constant times e to the alpha x is a solution. So we know y equals e to the alpha x solves our differential equation. Then it's quite a standard technique with differential equations. Once you know one solution to your differential equation, you could try modifying this. So we could try multiplying this e to the alpha x by some other generic function f of x, and see if this will tell us some information about f of x by substituting this back into our original differential equation, and it could lead to a more general solution. So I don't think this is a particularly obvious step to think of, especially if you're quite new to differential equations, but this is quite a standard technique, and as we'll see, when we differentiate y, and we differentiate again using the product rule and substitute back into our original differential equation, you'll see that because e to the alpha x is known to be a solution to our original differential equation, we'll get lots of nice cancellation, which then allows us to glean some information about this new f of x function. We've got y equals this, and then if we want to find the first derivative, we just differentiate using the product rule, so we get alpha e to the alpha x times, I'm just going to write f rather than f of x, and we've also got plus e to the alpha x times the first derivative, f prime of x. Then we can factorise all of this just to make it a bit easier, so we have alpha times f plus f prime all multiplied by this common factor of e to the alpha x. So this is our first derivative, and then to find our second derivative, again we can use the product rule here. So our second derivative, when we write all of this out, let's differentiate this first. So we get alpha times f prime plus f double prime times e to the alpha x, and then differentiating the e to the alpha x terms just adds another factor of alpha here. So we get alpha squared f plus alpha f prime times e to the alpha x. And again, we've got e to the alpha x as a common factor of everything, so we can just factorise all of this and get the second derivative then can be written as, let's write alpha squared f plus 2 alpha f prime plus f double prime all multiplied by e to the alpha x. So we've got the first and second derivatives, and we can now substitute these into our original differential equation. And just before we do this, you can see that each of these have a common factor, e to the alpha x, and when we substitute in, we can just divide through by e to the alpha x and focus our efforts on f, because we know e to the alpha x isn't going to be equal to 0, so we can just divide through by that. So just to save a bit of space, I'll go straight to substituting in and dividing through by e to the alpha x. So our second derivative term here becomes alpha squared f plus 2 alpha f prime plus f double prime, and then we have minus 2 alpha multiplied by the first derivative, so multiplied by alpha f plus f prime, where again we've just divided through by e to the alpha x, and then finally we have plus alpha squared times y, so plus alpha squared times, then this is just f because we've divided through by the e to the alpha x term, and all of this is equal to 0. So now if we look at some of these terms, let's look at all of our f terms. We've got alpha squared f, and then here we've got minus 2 alpha squared f, and then we've got another plus alpha squared f. And all of these actually cancel, so alpha squared f plus alpha squared f minus 2 alpha squared f just gives us 0. So we're seeing some of this nice cancellation behaviour as a result of the fact that e to the alpha x is a solution to our original differential equation. And similarly, if we look at our f prime terms, we've got 2 alpha f prime here, minus 2 alpha f prime. So again, these terms just cancel, and all we're left with is f double prime, the second derivative of f, is equal to 0. So we get a really nice differential equation in the end, where we can just integrate this. So we integrate once, we get f prime x is equal to just some constant, which we can call b, and then our next one, when we integrate again, we're going to integrate this b term, gives us bx, and we've also got a plus a. So then our original solution was y equals e to the alpha x. We've looked for a different, more general solution by multiplying by e to the alpha x. So we get this more general solution then, and again, just swapping the order here, a plus bx, this gets multiplied by e to the alpha x. So this is quite a nice way of seeing, again, where this bx term has come from. It's just come from the second derivative of this f of x function has to be just 0, so we integrate this twice, and we get this a plus bx. And I think the only thing that's difficult about this method is seeing why would we consider multiplying by this function f of x. So let's have a look at another example then after this to understand where bx comes from that perhaps doesn't require this level of knowledge about differential equations. And now for our final way of understanding where this bx term comes from, we're going to imagine we've got two distinct roots, alpha and alpha plus epsilon, and then we'll try in some sense to take limits as epsilon goes to 0. So this isn't going to be particularly rigorous, but I think it's quite nice to see some of the underlying structure and make these connections with what's actually going on as one of the roots gets closer and closer to the other. And one of our issues here is how can we actually take limits as epsilon goes to 0, because we had a differential equation. What does it mean to take a limit of a differential equation? Well, to make this slightly more concrete, we're going to introduce some initial values, so that instead of working with these arbitrary constants a and b, we'll work with some values which are actually related to some fixed numbers. So let's say for our initial conditions, let's say that when x is 0, we'll say y is equal to some value a, and we'll say that the first derivative dy dx is equal to some other value b. So then we can use the fact that y is of this form, and when x is 0, y is a, we can just read off then a is equal to, when x is 0, these exponential terms are both 1, so we get lowercase a is capital A plus capital B. So this gives us some information about how our capital A and capital B are related to our initial conditions. So then for the first derivative being equal to b, let's just first of all differentiate everything. So we get y prime equals a alpha e to the alpha x plus b alpha plus epsilon e to the alpha plus epsilon times x. And then when x is 0, the first derivative is b, so we can write b is equal to, and again our exponential terms here are just going to be 1, so we can write b is equal to a times alpha plus b times alpha plus epsilon, so b times alpha plus epsilon in brackets. And now we've got two simultaneous equations which we could actually solve to find a nice expression for our capital A and our capital B in terms of this lowercase a, lowercase b. And you can see our a and b actually depend on epsilon, which I don't think is particularly obvious just looking at it in this form. But introducing the boundary conditions helps us to see that our general solution, our constants, do actually depend on epsilon in some sense. So I won't go through all the working for solving these simultaneous equations, but we can solve these to find capital A and capital B. So we can get that capital A is equal to a times alpha plus epsilon minus b, all divided by epsilon. And then our b, we have a slightly nicer expression. We get negative a times alpha plus b, again all divided by epsilon. And the reason we've done this is now we can write our general form of this solution with these general y equals a and the first derivative is b. Using this boundary condition, we can write this as our general solution is then y equals a times alpha plus epsilon minus b all over epsilon. This gets multiplied by e to the alpha x, and then our b term we have negative a alpha plus b all over epsilon, and this is multiplied by e to the alpha plus epsilon times x. And now we're in a state where we could potentially rearrange this and take limits as epsilon goes to 0 and see what we get. See if we do get this a plus bx kind of structure multiplied by e to the alpha x. So before we take limits, we'll rearrange and simplify this a little bit. So when we look at all of this, we've got a common factor of e to the alpha x. So we'll take this out as a common factor, put everything else into brackets, and you'll notice pretty much everything depends on epsilon. Actually, the only term we'll get that doesn't depend on epsilon is going to be this a times epsilon divided by epsilon. So we just get an a on its own, and then from this first term we're also getting an a alpha and a minus b all divided by epsilon, and then we're also going to get some more terms divided by epsilon here. So here we get we've also got this structure of a alpha minus b, but it's negative, so we can write this as minus a alpha minus b. Then this gets multiplied by e to the epsilon times x, and all of this gets divided by epsilon, and on the outside of the bracket we put our common factor e to the alpha x, just like that. And now you see we've got this common factor here of a alpha minus b, which means we can write this in a slightly nicer form of a plus a alpha minus b multiplied by, then we've just got 1 minus e to the epsilon x over epsilon, and this is still all going to be multiplied by e to the alpha x on the outside. So now we've managed to get our epsilon terms into quite a nice simple form here where we can take limits. So if we write this, maybe we could write this the other way round. So the negative of the limit as epsilon goes to 0 of 1 minus e to the epsilon x over epsilon. We can write this as the limit as epsilon goes to 0 of e to the epsilon x minus 1 over epsilon. And this is in quite a nice form, so we could use Taylor series expansion or L'Hopital's rule. You could even see this as a derivative of a new function of e to the t times x with respect to t, but one way or another we see that this limit is just actually going to be equal to x. And remember, this is the negative of what we've got here, so this, when we take limits as epsilon goes to 0, we're going to get negative x. So then we can rewrite all of this as a plus a alpha minus b, and then when we've taken limits as epsilon goes to 0, we just get a negative x. So I'll write this as negative 1 times x, and we've still got our e to the alpha x. So this is as epsilon goes to 0 in some sense, this is what we get. And now we can focus on trying to make this look like our more familiar forms. We've got this lowercase a term here, and we've also got this combination of constants multiplied by x. So we could relabel this as capital A or use a different letter since we already used capital A, and similarly we could relabel this one as capital B, and then we've got our general solution in some sense as epsilon goes to 0 is a plus bx all multiplied by e to the alpha x. So again, we haven't been super rigorous with this, but I think it's really nice just to see this connection and see that as the roots get closer and closer to each other, it does make sense that our general solution then shouldn't just be a e to the alpha x plus b e to the alpha x. We do get this extra x term when we consider this really carefully, introducing some general boundary conditions and taking limits as epsilon goes to 0. And I think it's not so obvious that your capital A and capital B there have to depend on epsilon at all or depend on the value of alpha, but then just introducing these general boundary conditions makes it a little bit more concrete, and this gives us another way then of understanding where this bx term has come from.